Good afternoon, students. Today we are going to discuss about the topic that is behavior of a conductor in an external electric field. That means when a conductor is placed in an external electric field, then what is the effect? How it's behave means what is the changes takes place inside this conductor. Let us discuss that one. Let us draw. This is the conductor. Say this is the conductor. This conductor is placed between the electric field. Say this is a positive. Say this is negative. So as we know that the electric field will run from positive to negative. In this direction, the electric field will move. So, in the presence of this electric field, in the presence of this external field, this is called external field. Say this is E external. So, in the presence of this external field, a conductor is placed. Then what happens? It is, as we know that the conductor is a neutral in nature. That is neutral in no charge. That is neutral. Neutral means what? It will have both equal and opposite charge. That means negative charge and positive charge will be there inside, but they will be get cancelled. So equal number will be there. So what happens? These neutral charged body, whatever the negative positive charges are there inside this electron will be, that means negative charge will come towards this positive charge like this. It will come. When the neutral body is kept inside an electric field, then what happens? The positive charge will attack the negative charge inside this neutral metal, whereas the positive charge will be repelled by this positive, and those positive will be attracted by this negative. Finally, this side a positive charge will be appeared. That means a polarization takes place. Positive and negative charge, they will be separated in such a manner. That means internally an induced electric field is created from right to left side. When external field is applied from left to right side, then the charge will be polarized. That means negative charge, positive charge, they will be separated. By separating from positive to negative, and induced EMF is said to be developed. So this induced EMF I will tell EIN. So this is called IND, induced current, induced electric field. So it was seen that how long this electric field will, how long the charges will be coming means as long as the electric field, the strength of electric field, how much electric field we are applying externally, that much of electric field has to be developed inside. Still then all the negative charges at this side and the positive charges that side will be it will come this side and the positive charge will move toward that side until the induced electric field should be equal to that of the external electric field. These two will become equal and opposite. Therefore, I can say that net electric field, that is the first point, it says that net electric field I will write this as a point wise. First point, net electric field inside the conductor is 0. So net electric field inside is 0. That meaning is inside this conductor, when it is placed in external electric field, inside net electric field is 0. That means net electric field means E net is equals to E external minus of E induced. I will write here E net. That means net electric field in this direction is equals to E external minus E induced. The difference between these two, that is the net electric field will be 0. Why? Because these two will become equal and opposite. So these two will get cancelled. So net electric field is 0. So this is first point. E net is equals to E external minus E induced is equals to 0. So keep in mind that whenever a conductor is placed in an electric field, then the net electric field inside the conductor will be 0. How it is 0? Why? Because whatever the external force, external field is applied, that much of induced field will be developed inside. So these two will get cancelled. So finally, net electric field in this will be 0. That is the first point. That is the first point. Now the second point. Electric field here always it will be normal to the surface. Even if the conductor is in a square shape or it may be in a irregular shape, whatever it may be, always the electric field will be normal to the surface of the conductor. That means, like you see here, it is always normal to the surface of a conductor. It is normal, always. It may be straight or it may be suppose some irregular shape. Then also the electric field will be normal only, normal to the surface always. So therefore, I can say electric field is always normal to the surface of the conductor. So this is the second point. So first point we can say that what is the first point is net electric field inside the conductor is 0, whereas the second is what? Electric field is always normal to the surface of that conductor. So this is the second point. Now third point, charge inside the conductor will be 0. Charge inside the conductor will be 0. That means whatever the excess charge is there, that excess charge will always reside only outside the surface. Excess charge inside the conductor will always reside only outside the surface. Inside the conductor, the net charge is 0. Net charge is 0. Why? Because net electric field inside is 0. Hence, net electric charge will also 0. For example, see here. For example, third point I am talking. Suppose say this is one charged conductor. Suppose say this is the one charged conductor. Suppose this is a conductor. Inside, as just now we have seen that when external field is applied, E net inside will be 0. Net electric field is 0. That means E inside will be 0. E net will be inside is 0. If this is 0, we know that one formula, the flux which is passing through this surface is equals to line integral of E ds. This is the formula. Flux is equal to E into ds, surface area. Okay, surface area I have taken. So here surface area, I can take this surface area. Suppose say this is the Gaussian surface I have taken. So this is called what? Gaussian surface. So inside this surface, electric field is 0. Inside this Gaussian surface, electric field is 0. So electric field is 0. And we also know that according to the definition of a Gauss law, flux phi is also equals to charge by epsilon naught. That means the amount of charge enclosed divided by epsilon naught. So as we know that net electric field inside is 0. That means this is 0. If this is 0, this implies that flux is also 0. If flux is 0, then from the definition that these two are equal, from this we can say that charge inside this also 0. As from the first definition, point, electric field inside is 0. If this is 0 means electric field is 0. If E is 0 means flux phi is 0. If flux phi is 0 means from the definition, flux phi is equal to Q by epsilon naught. Gauss theorem, Gauss law statement. If this is 0 means Q is also 0. Why? Because these two are equal. This is 0 means definitely charge inside will be 0. And we can say that inside this charge is also 0. So inside no charge will be there. So inside charge is also 0. E net also 0. So electric field inside is 0. Charge is also 0. When? If the if this conductor is placed in a external field. Okay. Now come to the point. So that we can say that charge inside the conductor is 0. Charge inside the conductor is, we can say that this is 0. Therefore, now next point. Electric potential, how inside it will be. Inside this conductor, let us see what about the electric potential. As we know that electric field E is 0. That means electric field E inside this conductor is 0. Inside the conductor, electric field is 0, I am telling. If electric field is 0, we are having the relation between electric field and electric potential. That is E is equals to dV by dx or dr, we can say. Here I am taking magnitude, I have not kept here minus, I am taking a magnitude. That is E is equals to dV by dx. As here E is 0, that means dV by dx also equals to 0. So the differentiation of something is 0 means this something, that means the differentiation of voltage with respect to the distance is 0. This implies that V should be constant. The differentiation of constant is 0. We know that differentiation of constant is 0. So this is 0 means I can say that this should be a constant value. So I can say that means V is constant. That means inside electric field is 0. Inside electric field is 0. This means that inside the potential will be constant at every point. That means at every point, if you take anywhere, if you take the electric potential inside this conductor will be constant when it is placed in an external electric field. So I can say that electric potential inside the conductor is constant. That is V inside is constant. Here charge inside is 0. So we are having this is now so right here we can see that the electric potential inside a conductor will be what? It is constant. And now see what is the electric field inside just outside the surface. What is the electric field intensity just outside the surface? That means at the just outside this surface, what is the electric field value just outside the surface? Let us see. So number 51, as we know that electric field E is equals to, or according to the Gauss law, I can say that flux phi is equal to E into ds. And also according to the Gauss theorem, we also know that flux is equal to charge by epsilon naught. We know this formula also. Therefore, from this it is quite clear that I will derive here only. As we know that flux phi is equal to E into ds formula, and from the Gauss theorem, this also equals to charge enclosed by epsilon naught. We know this one very well. Therefore, since that means flux which is coming outside through this area, that means I will consider this area, outside area. Here I wish to calculate the electric field intensity. Suppose this is the conductor. Here I wish to calculate the electric field intensity just outside the surface. That means say I am taking this is the point at which I wish to calculate the electric field intensity. So from this I will draw one Gaussian surface. So this is the Gaussian surface. This is the charge. Let us say this is the charge Q, which is enclosed in this area. So that means electric flux will be coming through this area. Definitely the electric field will come like this. That means electric flux is coming in this direction like this. So therefore, what is the electric field intensity at this point, at a particular point on this Gaussian surface? That we can calculate with this. The flux which is coming outside through this area is equal to E into ds, which is equal to charge by epsilon naught. This is the charge. This is the charge Q which is enclosed in this Gaussian surface. This much of charge is enclosed. So I can write charge by epsilon naught. Therefore, we know that sigma is equal to charge by area. Say that is ds. Okay, charge by area I can say it as a ds. Therefore, charge is equal to I can write sigma into ds we can write. So therefore, instead of this charge I will place here. Therefore, E ds is equal to sigma ds by epsilon naught. So therefore, here ds will get cancelled. Therefore, E is equal to sigma by epsilon naught. So the electric field at any point just outside this charged surface or just outside the conductor, E is how much means that much. That is sigma by epsilon naught. So electric field just outside the conductor, what is the electric field? E is equal to sigma by epsilon naught. So this is the electric field value. Got it? Now the next point. Now sixth point. Suppose say this is now let us see what is the electric field inside a cavity. Suppose say this is a conductor or hollow conductor. That means it is having some cavity like this. Say this is of some charge. So that means inside this is called cavity. Means nothing is there. The charge is only here. Okay, so this is called this is called cavity. So if I take this is a Gaussian surface, if I assume here one Gaussian surface, then according to this formula like this, if I draw one formula, what is the electric flux coming outside through this surface? That is formula flux is equal to E into ds, which is equal to charge by epsilon naught according to the Gauss theorem. That is the formula. But in this surface, is there any charge is there enclosed in it? Q is 0. No charge is there. Charge is only outside this conductor. That means in this cavity, no charge is there. Only the charge is here. So charge is here. So inside this cavity, there is no charge. So when charge here, since charge is 0, I can say that E ds is also 0. Charge is 0 means this will become 0. This implies that E also 0. So from that it is quite clear that since charge inside this is 0, this implies that E also 0. So inside the cavity also electric field is 0. So these are the few points which regards with the behavior of a conductor, which is says that the behavior of a conductor in an external electric field. So when a conductor is placed in an external electric field, what is the change takes place? So first point is what? Net electric field is 0 because external force, external electric field is equals to induced electric field. So these two will get cancelled. Therefore, the net electric field inside the conductor is 0 when it is placed in an external electric field. This is the first point. Second point, the electric field will be always normal to the surface of a conductor. However may be the shape of the conductor, whatever may be the shape of the conductor, but always the electric field will be the normal to the surface of a conductor. That is the second point. And the third point is charge inside the conductor is zero. Why the charge inside the conductor is zero? Because electric field inside the conductor is zero. Hence we can say that the charge also inside it is zero. From a Gauss theorem we can say. Similarly, fourth point. From the fourth point, it is very quite clear that electric potential inside the conductor will be constant. How it is constant? Because inside this conductor, electric field is zero. So electric field is zero means electric field is nothing but it is the dV by dx. That means potential gradient we can say E is equals to dV by dx. When E is zero, that means dV by dx also zero. So the differentiation of voltage, potential is zero. That meaning is potential is constant. So this is fourth point. And the fifth point is the electric field just outside the conductor. Just outside the conductor, how much electric field is there? Means if you apply a formula, that is flux is equal to E into ds, which is equal to charge by F1. Since here we know that surface charge density is equal to charge by area. From this, charge is equal to surface charge density into area. So I will substitute this value here. Therefore, ds got cancelled. Therefore, E is equal to this much. So from this, what we are going to say here, just outside the surface, electric field is directly proportional to the surface charge density. So from this, it is quite clear that electric field is directly proportional to charge density. So if you take a more charge density charge if you take on the surface, that much more electric field will be there at this point. If you take lesser charge density value of charge, then the electric field will be little weak. That means it says that just outside the conductor, the electric field is directly proportional to charge density. Charge density is more means electric field will be also more. So this is the fifth point. Now come to the point, that is sixth point. If you take a hollow sphere like or hollow conductor, if you take, that is, it is having a cavity. Cavity means this is the space in which no charge is there. Very clear that inside this there is no charge. Only the charge is just outside this cavity. That means from this we have a formula flux phi is equal to EDS into Q by epsilon naught. So from this it is quite clear that if I assume one Gaussian surface around the cavity, from this it is quite clear that inside this Gaussian surface charge is zero. That means charge is zero. If I put the charge as zero, that means this entire thing will become zero. This implies that E is also zero. That meaning that if inside this cavity, if no charge is there, this implies that electric field also inside the cavity will be zero. So these are the few points. These are the few important points to keep in mind. Okay. Now next topic is electrical capacitance. So still now we have read about the electric potential and electric potential energy, and after that we also just now we have seen that how the electrical conductor or how the conductor will behave when it is placed in an external electric field. Just now we have listed as 6 points. This is to be keep in mind. Therefore, now let us discuss about what is electrical capacitance. What is electrical capacitance? So what is electrical capacitance means nothing but it is electrical capacitance. It is nothing but it is the ability to hold a charge or to hold a energy on the conductor. Suppose one conductor is there. Suppose this is the one conductor. if I give some charge, how much charge it can occupy on it. That ability of holding this, of holding a charge of this conductor, it is said to be its capacitance value. So electrical capacitance of this conductor is nothing but it is the ability of this conductor to hold a charge on it or to store a electrical energy on it. So how much electrical energy or how much electrical charge can be stored by this conductor, that is called electrical capacitance. Okay, so here to better understanding this, let us have a small example. Suppose I am taking a small glass and once I am taking one more big glass. In this, suppose if I pour a water, in this also if I pour water, then what happens is, suppose here our water is increasing, the level of our water is increasing. Here also the level of our water is increasing. Finally, suppose say it has reaches here up to this much, but it has also reaches up to here. So in this both the cases, it is very quite clear that the water in this jar or in this jar is more when compared to that of the water in this. Here the water content is more. That means its potential is more. So here, how much potential is there means how much you have poured of water. So here, water is directly proportional to its potential. So how much water you poured on in this jar, that much of its potential is rising, increasing. Similarly, here also, if you have given a little water, so here only little potential is rising. Here you have given more water, hence we can say that here more potential is rising. In the similar manner, here also on a conductor, how much charge if you give to the conductor, that much of potential will be increasing on this conductor. So here conductor is nothing but it will behave like this jar like. Water is nothing but here like a charge. How much charge if you give, that much of it will hold. Then here the amount of water which is increasing, it is called potential. So here also how much charge if you give, that much of ability, suppose it has to hold more and more charge, then I can say that its potential is increasing more and more. So here very quite clear that here charge is directly proportional to potential. That means here water is directly proportional to its potential. How much water you pour, that much of its potential is increasing. Similarly, here also, how much charge you give to the conductor, that much of potential of the conductor will be increasing. So from this I can say that, from this we can say that charge is directly proportional to the electric potential. Therefore, charge is equal to, remove this proportionality constant, I have to equate and we have to place some constant. That constant we will say here as a C and V. This V I have written here. So from this here, this is called a constant. So this C is equals to, we can write here from this Q by V. So here this constant is nothing but is called electrical capacitance. So electrical capacitance means this is capacitance. Capacitance of a conductor. So how to define this capacitance of a conductor? Capacitance of a conductor can also be defined as it is the ratio of the charge to that of its potential. The amount of charge is given to the conductor and how much potential it has occupied, means how much potential it has raised. Charge given to it, how much potential it has raised. So that charge given by the potential rise will give the capacitance value. So this is called capacitance. Okay, therefore, in one way we can say that capacitance is nothing but what is capacitance? How much it is having capacity to hold the charge. So that means we can say that how much it can occupy the charge. That means how much it can hold the charge on it. So that is called the capacitance. Fine. Here, capacitance, it is having a unit. What is the unit of the capacitance? Is nothing but, this is charge, unit is nothing but coulomb. This is called volt. So capacitance SI unit is, what is that? Coulomb per volt. So coulomb per volt. See here, this C is not a capacitance. This is called capacitance. Here C is called coulomb, unit of the charge. Don't get confused. This C is called capacitance. This C is called coulomb. So I'm showing the difference. So I'm writing like this to get a difference between these two. Don't get confused. So coulomb per volt is called its capacitor, its unit, capacitance unit, which we call it as a farad also, which we call farad. That means 1 coulomb per 1 volt is called 1 farad, we can say. Or see, coulomb per volt is called farad. We know this one. We say that coulomb per voltage, this is also called as a farad, which is given by the name of the scientist. So this is called farad. So here, here 1 farad is a very larger unit of capacitance. So 1 farad is a very larger unit of capacitance. That means, what is the capacity of this conductor? Suppose if you say, then if I say this conductor is having a capacitance of 1 farad or 10 farad, 5 farad, 2 farad, if you say like this meaning is that much of 2 farad, 5 farad, that much of capacitance is a very larger capacitance. That means the charge has to be given very much large. So that much of big space is required to occupy the charge. So that much of capacitance. So it is a very much bigger capacitance. So that means, but in generally we don't use that much of bigger capacitance. So means what I am going to tell you is, here 1 farad is a very bigger unit or very larger unit of capacitance. So hence we use only smaller capacitance value or smaller units we will use. Instead of farad, we use only millifarad. That means 10 power of minus 3 farad, or I can say microfarad, which is equal to 10 power minus 6 farad, or we can say picofarad, which is equal to 10 power of minus 12 farad. So these are the smaller units which we use in our practically, means in our books or in our which we learn. In this we will use only this milli, micro, pico in this way. Means in terms of 10 power minus values only we use. We won't use 1 microfarad, 2 microfarad. Why? Because 1 microfarad is a very bigger unit. Let us see how much bigger unit. I will show you that. Suppose say I am taking a sphere. Suppose say this is a sphere of radius, say that is r. This is having a charge, say that is capital Q. Then what is the potential on the surface? What is the potential on the surface means potential on the surface is given by V is equal to 1 by 4 pi epsilon naught into Q by R. We know this general formula, we know this very well. And since from the formula, from this definition, I will write from this definition of capacitance, since we know that C is equal to charge by voltage. So therefore, charge means let it be charge. What is this value? V means I will write this value. This value I will write here. So therefore, 1 by 4 pi epsilon naught into Q by R. So this is equal to C. So here Q will get cancelled. Therefore, what is left here? C is equals to this entire thing will go up. Means 4 pi epsilon naught into R. So this is called the capacitance of this capacitor. So this here is having the capacitance. how much capacity it has means this much of 4 pi epsilon naught into R. If you know the radius of the sphere, you will get the capacitance value. Okay, so let us see how much bigger this capacitor is. That means how much bigger this 1 microfarad. This 1 microfarad is how much larger, let us tell you. For example, from this if I calculate R is equals to, from this R is equal to, I will cross multiply this. That means C by 4 pi epsilon naught if I write. If I write like this, what is here? C means just now we told that C is nothing but capacitance. Suppose if the capacitance is of 1 farad, as I am telling you that 1 farad is how much bigger, let me tell you. So instead of C, if I take 1 farad, capacitance of this capacitor, suppose say it is of 1 farad. See, this is of 1 farad. Therefore, divided by 4 pi epsilon naught. 4 pi epsilon naught. What is 1 by 4 pi epsilon naught? Its value, we know this. This is equal to 9 into 10 power of 9. So the radius we got how much is 9 into 10 power of 9 meter. So therefore, R is equal to 9 into 10 power of 9 meter. So this is the radius I am getting. So that means if you construct a sphere of this much bigger radius, then its capacitance will be of 1 farad. This capacitance will be of 1 farad. So when it will be 1 farad means if the radius of this sphere will be of 9 into 10 power of 9 meter. So that much of very bigger length you should have. 9 into 10 power of 9 meter is nothing but it is almost equal to the 1500 times of the radius of the earth. Whatever the radius of the earth is there, if that radius of the earth is equals to the 15 times the radius of the earth, then with that much of distance, if you can construct one bigger sphere, on that sphere whatever you can store the charge, that capacitance of that sphere is said to be a 1 farad. So very bigger unit it is. So hence we can say that bigger unit we won't use it. We use only smaller unit, that is millifarad, microfarad or picofarad. So these only we use. So 1 farad is a very bigger unit. How many? This much of bigger value. Got it? Now let us talk about principle of capacitance. Principle of capacitor. What is the principle of capacitance or principle of capacitor? Principle of capacitor we will say. Principle of capacitor. What is principle of capacitor? Principle of capacitor, to know this, let us draw first one diagram, then we will explain. Let us consider this is one conductor. This is one conductor of positive charge. Suppose say this conductor is saying, I am saying it as a conductor. So this is called a neutral, this is called a positively charged conductor. Suppose say another one I am taking a conductor B. Suppose say one more I am taking a conductor B. This is of a positive charged conductor, and this is neutral. Neutral means what? It will have both equal and opposite nature. Means neutral means it will have both positive as well as negative equal in number it will have. So finally it will be neutral, I can say. So when you bring this neutral conductor nearer to the charged conductor A, then what happened? The charge inside this will be get polarized. That means inside this whatever the negative charge is there, it will come aside towards this side, towards the left side to attack this positive. That means all the negative charges will come toward this side. And whatever the positive charge are there inside, it will be get repelled by this. That means it will move away from this. That means it will come right side to the B, right side to the B. So from this, if you see carefully, here it is from the diagram, it is quite clear that negative charge is on the B is nearer to the A conductor, whereas the positive charge on the B is little away or little far away compared to this, it is little away from this A. So this negative charge is nearer to it and positive charge is far away from it. So from this it is quite clear that here negative charge on B reduces the potential of B. See, potential means what? What is potential means? Suppose say this is one container like. Suppose I have given some. Say suppose this is a charged sphere. Suppose say I am giving some positive charge I have given. Suppose say a positive charge is given. If I give further positive charge, suppose if I pour further some more positive if I give, then this charge also start occupying these remaining places. So that means here the positiveness will be increasing. That means its potential, that means its V value will be increasing. As you give the same kind of charge, its potential will increase. Suppose if you instead of this, if you give a negative charge, if you give, then what happens? When you give the negative charge, then what will happen? This negative positive will get cancelled. So finally, the potential on this will be keep on decreasing. So whatever the charge is there, this charge only will be remaining, and these charge will be equally distributed. That means these charges will be equally distributed far away from each other like this. Only less positive charge are left. These are equally distributed. So here we can say that from this it is quite clear that if you give a negative charge, its conductor's potential will be decreasing. If you give the positive charge, its potential will be increasing. So here also the potential on the plate A will decrease due to this. Why? Because this is negative. It will try to decrease its potential, whereas this positive charge will try to increase its potential. So I can say here that potential on A decreases due to negative charge on B. Due to negative charge on B, and potential on A increases due to positive charge on B. So due to this positive, its potential increases. Due to negative, its potential decreases. Finally, which effect will be more? Whether decreasing potential is more or increasing potential is more. Means I can say that here decreasing potential is more. Why? Because here negative charge is nearer to the conductor. So its effect will be more than that of its effect. So increasing potential will be less, whereas the decreasing potential will be more. So I can say that here this will be more than that of this. That means decreasing potential on A due to negative charge on B is more than that of the increasing potential on A due to positive charge on B. So that means that means decreasing potential will be more than that of the increasing potential. So due to this decreasing potential, due to this increasing potential. So due to this decreasing potential will be more. Why? Because it is nearer. So it will decrease more. It is far. So it will increase its potential will be less. Why? Because this is far away. So hence we can say that finally we are getting that when we bring a neutral body towards the charged body, then it is seen that finally what happens? It is seen that decreasing in potential is to be observed. So this implies that net decrease in potential takes place. So finally, net decreasing in potential is takes place. So now what I will do is, now I will connect this side to the earth. Suppose this side I have given to a earthing I have given. That means what happened here, if I give this side to the earth is nothing but it is a big reservoir of charge. So it can give any amount of charge or it can take any amount of charge. So when it is earthed, that means this earth will provide equal number of negative charge, that is electron. So these electron will come here, then these electron will start neutralize this side charges. So these many electrons it will supply. So finally this will get neutral. So finally there will be no charge on this side. So on this side there will be no charge. So that means if you earth this right side of the conductor B, then it is seen that this side will be neutralized. So now what happens means, now the potential of this will be further decreased. Why? Because initially due to this some increase of potential is there, but now here no charge is there. Now that means its potential will be decreased furthermore. Now it decreases furthermore. So this implies that due to earthing a positive charge on B, the potential of A is further decreases. So initially when positive negative are there, due to this the negative effect is more, hence its potential is decreases. When I have given to the earth, now the potential that positive charge is not there. Now its potential is further reduced. So from here it is quite clear that finally what happens means potential what happens decreases. Potential of A is what happens decreases. So when the potential of A decreases, as we know the formula, Q is equal to CV. Q is equal to CV. So in this case, did I alter any charge in this? Am I altered any charge in this? Am I added any charge in this? Or have I taken any charge from this? Nothing. I have not done anything to this conductor. That means on this conductor, whatever the charge is there, it is same like that as it is. That means the charge on the conductor A is unaltered, not altered. It is as it is. But here what happens? Without altering the charge, its potential is decreased. Am I right? How? By bringing the another neutral conductor. So by bringing the neutral conductor, its potential is decreased. So I can say that here charge will be remaining same. So here potential is decreased. This implies that the product of these two is constant. Why? Because charge before and after this process, its charge is same. I have not altered. That means charge is remains constant. So this is constant. So therefore, when the V value decreases, this implies that the capacitance will be increased. So from this we can say that, so this is the principle of a capacitor. What is that? Now I will tell you in a word. The capacitance of a conductor can be increased by decreasing its potential without altering the charge on it. So here what I done is the capacitance of this capacitor increased by decreasing its potential. How? By earthing without altering any charge on it. On this, I have not altered any charge. Charge is remaining as it is. Simply by this mechanism, I have decreased its potential. Because of this formula, the capacitance of this conductor increases. So this phenomena or this process, this is called the principle of capacitor. So once again, I tell what is the principle of capacitor? Principle of capacitor states that the capacitance of a conductor can be increased by decreasing its potential by using what? Earthing. By earthing the neutral body which is kept nearer to this conductor. So in this way, without altering this charge, So this is called the principle of capacitor. This is to keep in mind, right? So right, whatever the remaining topic is there, let us discuss this in our next session. Okay, still then, bye bye.